Okay, I'm in two different streams now, and I want to end this stream, but I don't want to. So what I'm gonna do is, this is some high level shit. So you get to see my face on this stream, and you get to see my actual bro. Just say it, bro. Okay. Let's give this a shot. Not gonna do anything today. I'm not gonna getting off this chair till not gonna do anything today.
Fantastic. Fantastic. So first off, it's really great to have you all here today. I really appreciate it.
In this video, I want to teach you how I learned statistics quickly and deeply. I've been working at my job for 4 months now, and it showed me that there's still an ocean of topics that I don't know about, and that I needed to know about them yesterday. Learning on the job is expected, but I've seen that people who can do this fast are the ones that get noticed and make the most impact. I'm developing my own workflow for doing this, and I wanted to share it with you today. Whether you're already experienced with statistics or a total beginner, I think there's something here for everyone, especially since we're all grappling with the presence of AI in our lives. If you're new here, my name's Christian, and this is Very Normal, a channel for making you better at statistics. Let's get started. I got the idea for this video because I was recently asked to use a model that, up until then, I'd literally never heard of. It's called ANCOVA, or Analysis of Covariance. Maybe you've heard of it before. I hadn't. I've already gone through the process of learning it at work, but I made it a point to take notes throughout my entire process. What you'll be seeing is my literal thought process while I'm learning. The first step in my process is to get some sort of formula or representation of the model. If I need to use it, then I should know what it looks like and what it's saying, right? My go-to place is Wikipedia, so I'll just look up ANCOVA Wikipedia and go to the page for that model. This will work for very common models, but for something more niche or cutting edge, then I'd probably look to a textbook or the paper that proposed it. According to Wikipedia, ANCOVA is a general linear model that blends ANOVA and regression. I'm not really sure what blending means, but this at least gives me a solid background. I know that ANOVA can be viewed as a special case of linear regression, so maybe ANCOVA is the same as well. It compares whether the mean of a dependent variable are equal across one or more categorical covariates and one or more continuous variables. And the hypothesis test compares many means together at the same time. That's pretty similar to an ANOVA. Then they go into some intuition stuff, which I don't need right now. I just need the model specification right here. So here's what we got. I see there's a yij here, so it's an outcome with two indices. And there's also an xij here. So I assume that represents a covariate that has an association with the outcome, the continuous one mentioned above. There's also this weird x bar, which usually indicates some sort of average. So I'm guessing this term indicates that all the covariates are mean-centered in some way. Then there are the parameters. There's a mu here, a tau here with an I index, a capital B that's paired with a covariate, and finally an epsilon term, which usually indicates some noise that makes it hard to distinguish between group means. Notably, mu and capital B don't have group indices, but tau and epsilon do. So I know what things will differ between groups and which will be the same. And now that I know what they are, I need to go back to the article to see how I should interpret them. So J represents the index for the observation within the ith categorical group. I is for group, J is for a particular outcome in the group. Mu is a grand mean. It's like the average of all the outcomes across all the groups. So I think the x bar is also some sort of grand covariate mean. Tau is described to be the effect of being in the ith category. In statistics, effect usually refers to some sort of change. So tau represents how being a part of one group changes their average relative to the grand mean. In my field of biostatistics, this usually has to do with comparing a placebo group against a treatment group. Here it's comparing a group mean versus the grand mean, so it's slightly different, but similar idea. This tells me that tau is actually the parameter of interest here, since it tells us how the groups differ in some way. B captures the change in the average outcome associated with the covariates. The B here is more so to adjust for the effect of these continuous variables. And this epsilon term, this seems like an error term, similar to other regression models. I know what I needed for this step, but it doesn't hurt to scan the rest of the article. There's this pie chart here, which is a mortal sin against visualization. No, there's a nice plot here. I don't really like this way of visualizing linear regression, but it keeps me into what the model is saying. All the groups here experience the same change in the outcome for a change in the covariate. That's reflected in the B term. In this plot, the group means are different when x equals 0. But the article specifically says that it tests whether or not these are the same. So under the null hypothesis, the plot should look like this, while the original form represents an alternative where they're all different. I read through this article with a lot of my own background information, but another way you can do it was with AI. While I have a lot of reservations about using AI, I think that this step is a good use case. I usually use Raycast to do this. If I just ask AI about ANCOVA here, it spews out a bunch of stuff I don't quite need yet, but I do see the model specification here. If I take this and compare it against the Wikipedia version, I can see what parameters correspond to what and how I should interpret them. Hey, editor question here. For some of you, some of the things I'm pointing out won't make sense to you because you won't share the same background knowledge as me. And I'm sorry if you don't quite understand everything, but the point of this video is to show you my learning process, not to teach you ANCOVA specifically. If you could just take one thing away from this video, I hope that fast and deep learning comes from developing a dense network of knowledge and adding to it over time. This video showcases specific actions and questions that I ask myself to cultivate that. It might look different case to case, but this is the general process. An unfortunate byproduct of turning this into a video is that it can give the illusion that this process only takes a few minutes. But in reality, I spent a good part of the workday going through this entire process. More difficult concepts have taken several days even. The next step in my process is to find actual use cases for the thing I'm learning. Step 1 provides a purely statistical view of the model, but I need to be able to apply it to specific projects and understand how to talk about it. The Wikipedia article did provide a use case, but there's no numbers associated with it, and it's not in my industry. I work as a statistician in the pharmaceutical industry, so the most natural examples that I look to are clinical trials. Clinical trials are a great place to learn from because they're highly regulated, which means that the statistical rigor expected from them is much higher. Recently, I've been seeing a lot of news about Novo Nordisk. They're the company behind one of the most consequential drugs developed in recent times. The technical name for Ozempic is semaglutide, or as I'll be calling it throughout the video, SEMA. One of the most important trials for SEMA was the Step 1 trial. Step 1 was a part of Novo Nordisk's registration package to get SEMA approved in the United States, and it specifically looked at weight loss in the obese and overweight population, measured as a percent change in the weight compared to baseline. Of course, Novo Nordisk was interested in proving that SEMA would result in more weight loss, and 2, which both compared SEMA against placebo for weight loss. I can see that they estimated that SEMA produced a 12% drop in weight adjusted for placebo. So this negative 12% has to correspond to somewhere in the ANCOVA model. Since treatment group is categorical, it most likely corresponds to the tau. This is the parameter that Novo Nordisk would be the most interested in, and seeing that it had a low p-value. But looking at the model, there should be some covariates added to the ANCOVA. So for completeness, I want to know what they are. I couldn't find them on clinicaltrials.gov, so I went back to the published manuscript of the trial. Since tau is the main thing that Novo Nordisk would want to report, it's unlikely that they would report the coefficients for the other covariates. They more for adjustment. After reading through the document, I found what I was looking for. Table 2 summarizes the information on all their primary and secondary endpoints. And in the footnotes, you can see this. Continuous endpoint analyses were conducted with the analysis of covariance method, with randomized treatment as a factor and baseline endpoint value as a covariate. So they adjusted for a single covariate in their ANCOVA, and it was the baseline measurement for each endpoint. This would control for the fact that everyone in the trial starts at a different weight, and I can see how this might influence how much weight they would lose throughout the trial. Furthermore, I want to highlight the slight change in notation here. Instead of using a grand mean mu, I've changed it with a beta 0 to represent the weight of the placebo group. Novo Nordisk was interested in seeing how well the treatment compared to placebo, not against a grand mean, hence the switch. However, this was an ANCOVA with only 2 groups, placebo and SEMA. The Wikipedia article made it sound like ANCOVA would easily come from more than 2 groups, and I wanted to see how a company might report something like that. To save some time, I'll just show you the example that I ended up finding. It was another SEMA study, except this one was done in people who have type 2 diabetes. Specifically, Novo Nordisk was trying to figure out how blood sugar and blood weight change with multiple doses of SEMA, 2, 8, and 16 milligrams, while comparing them to a fourth group, placebo. In the results section, they clearly posted ANCOVA in the analysis approach. But this time, you can see that there's multiple comparisons against placebo. There's one for 2, one for 8, and one for 16 milligrams. Each of these numbers represent a different tau in the ANCOVA. And thankfully, they made it easier to see what specific covariates were included in the model: sex and baseline HbA1c. To be honest, when I was still learning, I didn't even know that Novo Nordisk had used ANCOVA in their trials. I literally just looked up semaglutide on Google and got lucky with the first results. But you can do this with other companies as well. Step 3 in my process is to start working with code. The first 2 steps really involve being a statistics consumer, just reading about and understanding the model itself. Ultimately, I'm going to need to be able to use it in my own projects. So I need to be a statistics user. This means I need to be familiar with the statistical programming for ANCOVA. Similar to step 1, this can be done by either Googling R ANCOVA or Python ANCOVA, or you can just ask AI for a faster answer that you might need to check. If AI is good at anything, it's at providing code advice. Claude tells me that the AOV function implements ANCOVA, and it even gives me a helpful example to copy. Claude also tells me that I can use linear regression as well, which I already suspected. I've never used this AOV function before, so I'm going to dig into it a little bit more. The way I do this is by reading the documentation for the function. Sometimes online posts can be helpful as well, but in my experience, the documentation plus AI will get you most of the way there. The documentation tells me that the AOV fits an analysis of variance model and an ANOVA model. Furthermore, it just tells me that it uses the LM model, which implements linear regression. Should I be concerned? Not really. One of the unfortunate things about statistics is that a single model might be given multiple names. This is why it's important to look at the model specification first. In the end, ANCOVA really is just a linear regression with a specific set of covariates, a categorical variable of interest, and possibly many covariates that can either be categorical or continuous. So in that respect, Wikipedia was actually sort of wrong here. It focuses on the nature of the data itself rather than the question it can answer. This is why looking.
Dear fellow scholars, this is 2 Minute Papers with Caro João Naifa here. Finally, I have been waiting for quite Dear fellow scholars, this is 2 Minute Papers with Caro João Naifa here. Finally, I have been waiting for quite a while to cover this amazing paper, which is about AlphaZero. We have talked about AlphaZero before. This is an AI that is able to play chess, Go, and Shogi, or in other words, Japanese chess on a remarkably high level. I will immediately start out by uttering the main point of this work. The point of AlphaZero is not to solve chess or any of these games. Its main point is to show that a general AI can be created that can perform on a superhuman level on not one, but several different tasks at the same time. Let's have a look at this image where you see a small part of the evaluation of AlphaZero versus Stockfish, an amazing open source chess engine which has been consistently at or around the top computer chess players for many years now. Stockfish has an ELO rating of over 3200, which means that it has a win rate of over 90% against the best human players in the world. Now interestingly, comparing these algorithms is nowhere near as easy as it sounds. This sounds curious, so why is that? For instance, it is not enough to pit the two algorithms against each other and see who ends up winning. It matters what version of Stockfish is used, how many positions are the machines allowed to evaluate, how much thinking time they are allowed, the size of hash tables, the hardware being used, the number of threads being used, and so on. From the side of the chess community, these are the details that matter. However, from the side of the AI researcher, what matters most is to create a general algorithm that can play several different games on a superhuman level. With this constraint, it would really be a miracle if AlphaZero were able to even put up a good fight against Stockfish. So, what happened? AlphaZero played a lot of games that ended up as draws against Stockfish, and not only that, but whenever there was a winner, it was almost always AlphaZero. Insanity. And what is quite remarkable is that AlphaZero has only trained for 4 to 7 hours only through self-play. Comparatively, the development of the current version of Stockfish took more than 10 years. You can see how reliably this AI can be trained. The blue lines show the results of several training runs, and they all converge to the same result with only a tiny bit of deviation. AlphaZero is also not a brute force algorithm, as it evaluates fewer positions per second than Stockfish. Kasparov put it really well in his article, where he said that AlphaZero works smarter and not harder than previous techniques. Even Magnus Carlsen, chess master extraordinaire, said in an interview that during his games he often thinks, what would AlphaZero do in this case? Which I found to be quite remarkable. Kasparov also had many good things to say about the new AlphaZero in a, let's say, very Kasparov-esque manner. And also note that the key point is not whether the current version of Stockfish or the one from 2 months ago was used. The key point is that Stockfish is a brilliant chess engine, but it is not able to play Go or any game other than chess. This is the main contribution that DeepMind was looking for with this work. This AI can master 3 games at once, and a few more papers down the line, it may be able to master any perfect information game. Oh my goodness, what a time to be alive. We have only scratched the surface in this video. This was only a taste of the paper. The evaluation section in the paper is out of this world, so make sure to have a look in the video description, and I am convinced that nearly any questions one can possibly think of is addressed there. I also linked to Kasparov's editorial on this topic. It is short and very readable. Give it a go. I hope this little taste of AlphaZero inspires
This I got to do a workshop with you all last year, and it was a lot of fun. fun. So I appreciate getting to do it again. And so last year I gave a talk on for the MC Summer Institute on optimal control methods. It's an optimal control modeling, which I enjoyed giving, and it's still online if you want to check it out. But one of the things that we kind of took for granted when I did that workshop was that you all know how to simulate the movement of an organism, an animal, a robot in my case. So we decided to sort of back it off a little bit this year and have our topic be about how you simulate movement from scratch. Because I don't know about you all, I'm not sure when in your education you learn how to write computer simulations of movement. I mean, I'm an engineer. By the way, hello. Let me start over here. Hello, I'm Christian Hubicki. I'm an associate professor of mechanical engineering. It doesn't say biology in my title, but I love collaborating on biology projects. Oh, there are many ways that biology applies to many different disciplines and movement science. So I'm going to talk today about about how you simulate movement, because simulation is something you do a lot in my field. So, you know, many of us know all about, have seen a lot of Monica's work. Make sure we get this going here. All right. So here's an example of a thing that moves. Monica's, I don't know if it's your original research subject, but probably one of your most famous is the guinea fowl. We've seen many videos of these things running around on obstacle courses very stably, and they move, right? And experiments are so important for getting data out of animals. And I was actually put on a project working on this with Monica back when I was a grad student. But my field is less about animals directly and more about my subject, robots. I work in robotics. Okay, so where do we connect on this? And a lot of it is in the field of simulation. How do we make a simulation of an animal? Okay, in a way that's helpful. And why would you want to do that? Okay. And well, in robotics, the reason we want to have simulations is we want to be able to write controllers. And so one thing we will do is we will take a robot, we'll write a computer simulation, and have an algorithm try to optimize how the simulation moves to come up with a controller for a walking robot. And that's what this here is. So the first thing we had to do before we controlled this robot was how to simulate it. Okay, and so that's my specialty, and particularly the optimal control thereof. But more importantly, for I believe the Summer Institute, that simulations are math models, right? It offers another way to look into and interrogate the motion of organisms. If you have a simulation, you can try all kinds of things you would never think of trying with an animal, and test all kinds of hypotheses as to why the animal is doing what it's doing without an experiment, or more importantly, in complement with an experiment. Probably very, writing this paper that Monica had written back in 2006, she used a pretty simplified math model right here. What's called a spring-loaded inverted pendulum to model how this guinea fowl steps into an obstacle and then falls forward, and yet still maintains its stability. Okay, so simplified, and to do that, Monica had to write a computer simulation of movement, right? And from my standpoint, from a robotics standpoint, math models are also important for how you design robots as well as control them. If you have some simple bio-inspired model for simulation, something simplified, you can use it to inform how your robots are built as well as how to control them. And theoretically, if you have a reasonable bio-inspired model that guides your control and your design, you can end up with animal-like movement as a consequence. At least that's a hypothesis we've seen that we've toyed with a lot in the past. And math models can come in all shapes and sizes, right? This is OpenSim. It's been downloaded hundreds of thousands of times. Which allows your models to be complex and musculoskeletal. And probably is what a lot of people might think of when they're thinking of simulation is these really complicated models. But they can also be incredibly simple. This is a very simple model of a predator-prey interaction model by my student Jacob Hackett. The idea is that this little rat is running away from some kind of owl that's chasing it down. And you have a very simplified model, which is just a little mass that's being pushed around by a force, and they're trying to avoid each other using optimal control, right? So you can also use optimal control. You can also use models with optimal control